All right, so hello everybody. Thank you for being here. It's my pleasure to introduce Dr. Christina Vanderwel. Dr. Vanderwel is an associate professor and a UKRI Future Leaders Fellow in Aerodynamics and Astronautics Department at the University of Southampton in England. Her specialty is experimental fluid mechanics and turbulence and dispersion, and she's particularly good at doing experiments with lasers and PIV and fluorescence and things like that. So hopefully we'll see some of that in her talk today. She received her undergraduate degrees from the University of Ottawa, first studying coherent structures in uniformly sheared turbulent flows, and then looking at turbulent diffusion in uniformly sheared flows. And for this, she received the prestigious Pierre Laberge Award for Outstanding Achievement in Science and Engineering. And then she left North America to go to England, to Europe, because she received the prestigious Marie Curie Research Fellow at the University of Southampton. And they were lucky enough to hold on to her there. And now she's an associate professor there. So without further ado, I'd leave it to Dr. Vanderwel.
Thank you very much. That was a very nice introduction. I'll manage to share my slides now. We go PowerPoint, share. Oh, that's not working now, is it?
It is working, but I think it's the second screen, I believe. You have to screens? Yeah.
Let's start again. Because it worked the first time when I practiced with you, Karim, didn't it?
Yep.
Okay.
Yep, it's working now.
And if I make it full screen, now the slide is a full screen?
Yes, it is.
Excellent, thank you.
Thank you.
Okay, well, I'll get started now then. Thank you very much for inviting me. And what I'll talk about today is all about how we simulate urban flows in wind tunnel and water tunnel experiments here at Southampton. And this is what the images on this cover slide are supposed to portray. And on the left we have, this is the chimney. This is actually outside the lab when I was doing my PhD at Ottawa, and how it emits smoke into the atmosphere. And on the right is how we simulate that in the lab. And this is, we're using fluorescent dye as a proxy for air pollution in this image, and you can see that both of these scalars are being transported by a turbulent field, and that's the similarity. Before I go into all that, I prepared a background slide about myself, but I think Dr. Schwery just covered it all. So I actually did my undergraduate degree at Queen's University in Ontario before I moved to Ottawa. And it was in Ottawa, that's where I worked with Dr. Schwery. So I did my master's and my PhD at the same time as him, working on experimental fluid mechanics questions in turbulence. And I have the beautiful picture of the Ottawa campus on the top, and then also the beautiful picture of the Southampton campus on the bottom, which is where I am now. I think every campus has a beautiful picture like this, I suppose. The main difference, I would say, between Southampton and Ottawa is, so Southampton is in the south of England, and it never gets below freezing here, so we don't get very much snow. And in a way, I miss snow, but in a way, I kind of don't, so that's okay. As Dr. Schwery said, I got a Marie Curie Fellowship when I first came here to Southampton, working on turbulent boundary layer flows. And now, as an associate professor, I have another fellowship by the UKRI, which is just the UK science research funding body, and it's to study urban flows and air pollution. And as I'll explain in my talk, that's sort of a natural progression from these fundamental turbulent boundary layer flows to studying urban flows, and I'll explain how it's the same thing. So And what's great about Southampton and what really drew me here in the first place were the excellent wind tunnel and water tunnel facilities. And we've just invested in a whole bunch more, and I can show you that on this slide. And so these brand new water tunnel and wind tunnel facilities were installed last year, actually, so over 2020 and 2021, a little bit delayed because of COVID, but wasn't everything. And it's just really great place to work. So in the left picture, there's me and my postdoc and one of our PhD students going hooray, because we have finally our water tunnel facility is ready and could be filled with water. And it's just a great facility for doing these sort of experimental fluid mechanics research. It's 8 meters long, the test section, 1.2 meters wide, and can be filled to 80 centimeters deep. So we can fit a lot of aerodynamic models inside, and as I'll show you in the talk, we also use it for boundary layer research. And then in the same building, but upstairs, we also have a brand new boundary layer wind tunnel, which is really cool because it's got a 10-meter long test section. And the test section takes up the whole of the upstairs, and then it turns 90 degrees through a hole in the floor, turns another 90 degrees, and then the fan is downstairs. So the downstairs lab is quite noisy because unfortunately it has the fan, but it means the upstairs lab has this just tremendously long test section, which again is just excellent for our boundary layer research, which we do at Southampton. And so in general, these are some of the research interests that I work on at Southampton. I work on turbulent structures, like Dr. Schwery said, building on the coherent structure research that I did as a graduate student. But now I also work a lot on atmospheric flows. I integrate mixing and dispersion, so both looking at outdoor air pollution transport as a mixing problem, but more recently also looking at indoor air pollution, or maybe virus transmission, which happens if air mixing in indoor environments. And another topic that I research as well is secondary flows, which can sometimes form in these sorts of turbulent boundary layer applications. And I also, before I get onto my talk, I wanted to promote the fact that this year I've also spent my time writing a new textbook on turbulent flows with my colleague Ian Castro. And we just got the proofs for the book this week, and it's due to come out next year. So if you are a fan of turbulence, then please keep your eyes open for it, because it will be an ebook available through the IOP publishing, and maybe your university already subscribes. So that's great, because we haven't had a good turbulence book since Pope's books, or Metzier and Scott are good textbooks, but that's been quite some time. So hopefully this will fill a gap in the market. Okay, moving on, I will now start talking about atmospheric flows and how we study them at Southampton. And here's the outline for my talk today. So I thought I would start by talking about the current challenges in urban flows, so why I'm studying them at all. I'll then talk about two specific case studies that I've worked on at Southampton. One is an idealized fractal city, which is a make-believe city that we made up just so we can get some general insights that are hopefully applicable to many cities. And then the second one is a realistic model of a real neighborhood in Beijing, which has tall buildings, and we wanted to focus on that neighborhood to see the influence of tall buildings on air quality. So after I've gone through those two case studies, I'll just have a few brief slides about what we're looking forward to doing next here in our lab at Southampton. Okay, so why do we study urban flows and air pollution? Well, this week is quite a big week in England. In Glasgow, the COP26 conference is going on, all about climate change and air pollution and that sort of thing. So if you're familiar with that, maybe I don't need to show this motivation slide. So what this slide is saying is that more than 80% of people living in urban areas are exposed to air quality levels that exceed the World Health Organization limits. And with more and more people living in cities now, this is clearly a big problem. The latest figure I saw was that more than half of the world population lives in cities. So this is quite a large portion of our world population that are being exposed to these unsafe levels of air quality. So obviously reducing air pollution is a big concern, and modeling this air pollution is also important so that we have the information to make these policy decisions. So not only is modeling important for forecasting the air quality, but also it informs these decisions that policymakers at places like COP26 are making right now. So how do we model air pollution, and how do we model atmospheric flows? Well, I'm interested in this problem because it's essentially a huge fluid dynamics problem, and you can consider the atmospheric boundary layer as essentially just a canonical turbulent boundary layer, except that it's over a rough wall instead of a smooth wall, and because you can think of buildings and trees as surface roughness. And when you look at it this way, you can see how knowing the wind profile, which is sketched here, obviously it's slower near the ground and goes to a quite fast free stream at the outer edge of the atmospheric boundary layer. So knowing this wind profile is important for predicting urban climates, for wind comfort, pedestrian wind comfort, for building wind loading, designing wind turbines, and also clearly pollutant dispersion at the ground level. And so basically the way it's currently done is using numerical weather prediction models. So the typical approach for numerical weather prediction is to divide up the world into a grid, both horizontally and vertically, and do a CFD calculation on that whole grid. Typically for numerical weather prediction models, the grid cells are on the order of 10 kilometers. But I think the American model is maybe about 5 to 10 kilometers for the grid scale. And the UK unified model, where it gets its most refined, gets as refined as 1.5 kilometers square as the grid cell. And so you would have this grid cell as you have on the right side of the screen here, and you have to then balance using your CFD code the flow that goes in and out of that grid cell, as well as the temperature and momentum and heat fluxes. And it gets tricky at the surface. So at the surface, obviously we don't have any flow going up or down, but you do have surface variables, and you need to know things like the net drag, the shear stress that the surface makes on that grid cell, as well as the net heat flux in that grid cell, which will be determined by the albedo of the surface. And the drag will be determined by the surface qualities of the surface. But recall that the grid cell is anywhere from 1 to 10 kilometers square, so you need the average drag over this square. And so what most of these models do is essentially just classify the type of surface in each grid cell as one of these different definitions of the local climate zones. So either they'll say that grid cell is tall buildings, that grid cell is industrial or forest or farmland or desert or water, for example. And then you use those surface conditions to then essentially determine the wind profile. So how does that work? This slide shows a nice picture of how the wind profile changes over the different surface conditions. And so over a rural surface, normally the wind profile is estimated by a log law. And the wind profile obviously changes if there's buildings, big buildings and big roughness. And so what we have is what we call a roughness sublayer in the bottom part of the wind profile, and then only farther up do we get this log law. So the trick that weather prediction, numerical weather prediction models need is if you know the surface properties, then what is the log law that we expect of the wind profile above it? And yeah, so those coefficients for the log law depend on the surface properties we have. And so we can summarize the different scales in meteorology by this picture. The top one, the mesoscale, is the big picture. And the approach here is to assume that the city is some sort of uniform, homogeneous roughness like we just described, and that we know what the log law looks like above this. And the problem with this, although it works with the big grid cells, is that you don't get any of the details in the city from this picture. If you zoom right in, so that would be plot C, picture C here, this is the microscale picture. And here, I mean, you're looking at the buildings, the individual buildings, and looking at the individual wakes of those buildings. And this is the other extreme in fluid mechanics, is resolving the individual wakes of each building. And this has also been done quite a lot in experimental fluid mechanics, and I can think of the papers by Martin Nuzzi and some by Castro, for example, that looked at these microscale flow features. But in between is the local scale, where it's quite difficult to model everything that's going on, and the wakes of multiple buildings might be interacting, and there might be urban canyons channeling the flow. And unfortunately, this is the scale that urban air pollution is transported. This is the scale that's relevant for when you're talking about air pollution, because you'll have, say, maybe a road source that's transported over a neighborhood, not just around one building. And if you zoom out to the whole city, you lose that detail. So a recent UK report highlighted this current need for new frameworks designed to treat heterogeneous surface exchange at scales ranging from the 100 meters to kilometer scale. And this is because this is where large eddy modeling is going. And so we need some wind tunnel modeling to fill those gaps. So that is what I'm going to talk about today, what we've been doing with wind tunnel modeling to look at the local scale features of air pollution in urban flows. So let's go right into that first case study. And this is the fractal case study of our fractal idealized city. So the objective of this study was, well, how well to do these homogeneous surface assumptions work when we have multi-scale distributions. So as I said previously, the way things are done now is you assume that inside your grid cell are all tall buildings, or all short buildings, or all forest, or all water, smooth water. And if you have buildings, then you would typically use the frontal and planform solidities of your neighborhood to then have the homogeneous surface properties for that grid cell. But say you have small buildings and tall buildings at the same time. So our fractal design takes this to the limit, essentially. It has big buildings and then smaller buildings and smaller buildings following a power law height distribution in a fractal pattern. And you'll see this is essentially a Sierpinski carpet fractal that I've arranged these buildings in. And so we're taking this model and now taking it in the wind tunnel to see what the flow profile is like. But not only did we study the organized pattern, I also took the exact same number of buildings and then rearranged them as in 4 random arrangements. So I called that A, B, C, and D. A has all the buildings just randomly placed in the same area, but quite spread out. And then B, you'll see that they're a little bit squished in the cross direction, and then C and D are even more squished. So D has it's the highest frontal solidity. The solidity is effectively changing with these 4 arrangements. Okay, so I have 5 patches now that I want to test in the wind tunnel to see what happens. So this is a sketch showing what the wind tunnel test looked like. This was in our old 3-foot by 2-foot wind tunnel, and we installed the 3D printed patch in the sort of later half of the test section on the floor. And underneath the patch was a force balance so that we could measure the drag, and that's essentially measuring the shear stress that the patch gives to the flow, or the drag that the flow gives to the patch, right? It's the same way going back and forth. And in addition to the drag balance, we also did PIV. So in this setup, the laser was positioned above the wind tunnel, and it was shot through a window at the top of the wind tunnel. And it was, in one experiment, it turned into a streamwise plane that highlighted the streamwise vertical plane of the flow in the center of the patch. And in another experiment, it was turned 90 degrees, and it highlighted the cross section of the wake behind the patch. And so there were 2 PIV experiments to capture the velocity fields in those 2 planes. And with the size of the building, which the biggest building in this setup, it was just a 1 centimeter cube. And with the wind velocity that we can get in the wind tunnel, which was about 30 meters per second, that gives us a Reynolds number representative of the tallest cubes of about 10,000 to 20,000, which is well in the turbulent range. Definitely not atmospheric boundary layer, big Reynolds number values, but we would hope that because they're square bluff bodies, that the shedding patterns that they make would be similar for all Reynolds numbers in the turbulent regime. So those are the wind tunnel tests, and to be fancy, I also did water tunnel testing. So this was in our old water tunnel, actually. It's not too different from our new one, but I took the exact same patch and put it in our water tunnel, and that allowed me to use fluorescent dye as a proxy for air pollution. Now, as it happens, if you take the exact same patch, so the height of the cube is still 1 centimeter, and put it in the water tunnel, our water tunnel can only reach a speed of maximum 1 meter per second, because it's water, but the density is so much greater. So what we find is that the Reynolds number is not too far different from the wind tunnel Reynolds number. So our Reynolds number of this flow was about 5,000, which again, it's on the turbulent side, so we can expect good comparisons here. For our water tunnel experiment, we also use a laser. And the laser is shined, reflected by some mirrors through a plexiglass plate that's aligned with the free surface, and then forming a sheet over the patch to illuminate the fluorescent dye that we inject ahead of the patch. And so that's how we can see essentially the air pollution patterns over this patch. So let's look at the results now. These are the drag measurements that we got from the wind tunnel. And I've color-coded them. So we have red is A, blue is B, green is C, yellow is D, and then black is the Sierpinski carpet arrangement. We can see those measurements here. The drag measurements are in grams by the force meter over the Reynolds number, which I varied by just changing the wind tunnel speed. And this isn't a very nice way of showing this plot, so a better way is by calculating the coefficient of drag. So it's normalizing these drag values by half rho v squared to get the coefficient of drag. And we can see here that over this Reynolds number range, actually, the coefficient of drag is fairly constant, as we just argued it should be in the turbulent regime. And the drag is ordered in the order A, B, C, D, with the Sierpinski carpet pattern sort of stuck there in the middle. And if we extract that, I told you that the 4 patterns that I made were ordered with solidity. So if I plot those coefficient of drag values versus the frontal solidity of each patch, actually we find the 4 random arrangements fit very nicely on a curve. And it's this Sierpinski carpet organized pattern that falls off the curve. And so this is really interesting finding that surprised me when I found it, is that actually we could, these rules that are used that predict the drag just based on the surface properties, they do in fact work quite well if there's a random arrangement of the surface roughness. But as soon as you start lining up your buildings in rows, then you fall off the curve. And I think that's insightful when dealing with cities, because clearly some cities do line up their buildings along streets and avenues. So again, maybe this is where we need to focus our research in these sorts of cities that do not follow the bigger pattern. So what did the PIV measurements tell us? Here's a snapshot of what the PIV measurements typically look like. Here I've combined the streamwise measurement and the cross-stream measurements together, and you can see the sort of patterns that we were able to measure, where red flow is showing the free stream flow, and then blue flow is the slower flow that's in the wake of that city patch near the wall. So a good way to analyze this is by taking the mean velocity map and then subtracting the mean velocity map that we measured in the patch from the velocity map that we get when there is absolutely no city, so a smooth wall result. And so this gives us this plot here in the middle. This is the velocity defect, or the velocity deficit map, that's created by the presence of that city. And so this city is actually slowing down the flow locally, and that's the net drag that this city has an effect, the effect of the city there. So we see there's a small initial deflection around the leading edge, but then a reduction in the velocity of up to 40% from what would have been there if there was no city locally due to these buildings. And then we call the edge of this velocity deficit map the internal boundary layer that's formed by this city. And this internal boundary layer, you can also see it in the turbulence statistics. So this is the plot B, is the RMS of the velocity fluctuations above the city patch. And we can see that the city kicks up extra turbulence into the flow. And the edge of this turbulence map matches the internal boundary layer that we get from the velocity deficit. And so I said that you should be able to predict the coefficients of the log law based on just the surface properties. And so here is the log law that we measure over the 5 cities. And so the blue is the baseline here, and then here are 5 cities: D, C, B, Sierpinski, A, and the shift in the log law is the same as, in the same order as the drag that we measured. So this shift in the log law coefficient is directly related to the drag that we measured in the city. It's due to the change in wall stress, essentially. So that's great. We confirm this, and we also confirmed again that the organized arrangement is an outlier when you line these up. We also confirmed this with the cross-stream measurements of the PIV. So these are the wakes behind each of the 5 patches. So this is the velocity deficit behind each patch. And we can see that the wake gets wider and bigger, the net size, when you go in order D, C, B, and then Sierpinski should fit here in between B and A, and that's the same order that we measured with the drag. So that's good that we see that in the PIV measurements, and it's consistent with the drag measurements. Now, what about the water tunnel experiments? So this is what the fluorescent dye experiments look like. We have an instantaneous snapshot of what the fluorescent dye looks like as it goes through the city patch, and on the bottom is the average concentration taken I think it was about 1,000 of these instantaneous images and averaging them together. And what was really interesting, I thought, was that the plume boundary, so the edge of the concentration, matched quite well with the internal boundary layer thickness that we estimated from the PIV. So that's the yellow line here. The yellow line is the internal boundary layer thickness from the velocity, and the red line is the plume boundary, which we defined as 0.5% of the source concentration. And so that's actually good news because there are quite a number of models for how internal boundary layers develop in turbulent boundary layers in turbulent flows over roughness, and not so many models about how the concentration reacts. So that is giving us good food for thought for developing our future studies and linking those two variables together. So just to summarize what we learned from that case study, first of all, that the frontal and planform solidity are good predictors of drag, except when the buildings have an organized pattern. And secondly, that the internal boundary layer not only seems to govern the velocity profile, but also modulate the extent of dispersion. So now let's take a look at what a real city looks like. So we're going to look at the Beijing neighborhood in the next case study. And here is a SolidWorks model of the city that we're in question. And what it is it was a neighborhood of all low-rise buildings, and then they came in and built 8 tower blocks, or 8 or so tower blocks there. And clearly it's going to have an effect on the flow. So the objective of this experiment, of this case study, was to see the impact of the tall buildings on the flow structure and the dispersion. And we also teamed up with colleagues at the University of Reading and Imperial College London, both universities in the UK, to compare the experimental results with large eddy simulations, which are a CFD model, and see if we could use our methods and compare the results. We also had 2 different model sizes this time. Again, the Reynolds number is in this order of about 10,000. So we don't expect much difference here, but we just wanted to double check. So this time we did just water tunnel testing. We put the model in the water tunnel. So here's an illustration of the model placed in there. Here's a picture of it at the bottom of our water tunnel. We've shown the laser from above as before. You can see it here going through that the plexi plate aligned with the free surface. And we have a tank of rhodamine dye which feeds our injection just upstream of the patch. We did simultaneous PIV, so the velocity measurements, and PLIF, which is the laser-induced fluorescence concentration measurements. And here's what it looks like. So these are the PIV measurements in the center plane of this city patch. We have the mean velocity on the top and the turbulent velocity variance of the streamwise component at the bottom. And what we see is the very first building that's in the measurement plane. So this one is a shadow of a building, but this building here is actually inside the measurement plane. So it's cut by the laser here, and that kicks up a huge wake and completely dominates the flow structure of that neighborhood. And we can see that in the mean velocity map, but also in the turbulent velocity map, because it just kicks up a load of turbulence as well into the atmospheric boundary layer. And what we think is happening is that this tall building is completely dominating the flow structure. The tall building creates some near wall turbulent action, which we can kind of see as the red spots in between the buildings. But the dominant thing here is the tip vortices. There are also going to be span-wise vortices, but I don't think we're capturing them in our measurement plane. We can see these also show up in the concentration measurements. So this picture here on the top right is the mean concentration, and we can see that even though the pollution was injected at ground level upstream of the city, it seems to stay at ground level until the wind impacts this first tall building, and then suddenly we have this chimney effect and it's spread right out and starting to ventilate into the atmosphere. We can see this even more clearly when we plot the turbulent scalar flux. And so what the turbulent scalar flux is the vertical velocity fluctuation multiplied by the concentration fluctuation. And then when you take the average of that, this is essentially the correlation between the vertical velocity and the concentration, which represents the net turbulent flux in that direction. And we can see that the tall building again kicks up this flow, which is then essentially ventilating air pollution out into the atmosphere. So I would say that's a good thing. So I think that's really interesting how dominant the tall building effect is. Now here are the two scale models that we made. We had a 1 to 2400 scale and also half of that size, and we've repeated the measurement. So here's the mean velocity measurement, the concentration measurement, and the turbulent scalar flux measurement of the two cases, and I would say that I'm satisfied that there's Reynolds number independence there, that the flow structures are the same for those two cases. And then what did we learn by doing the large entity simulation at the same time? Well, we were able to validate the large eddy simulation because our experimental velocity map, which I show here on the top, matches what the large eddy simulation predicts, that the tall building essentially kicks up the wake and is quite a dominant influence on the flow structure. But LAS also lets us see all properties of the flow at all positions in space because it's a computer model. So that lets us see, do this rendering on the right-hand side of the isocontours of the concentration. And we can see that it is released upstream from this point and seems to stick quite close to the ground until we impact the first tall building, and essentially has like a chimney effect and is really shooting that pollution out into the upper atmosphere. I think LAS is quite remarkable that you can do these sort of renderings with them. So what did we learn from this case study? First, that the rooftop shear layer from the tall buildings is a dominating feature that drives vertical fluxes. And secondly, actually, that we learned that the flow around the tall buildings is not too sensitive to the incoming flow conditions and to the Reynolds number. So that's actually quite a good thing for doing our experiments, and also a good thing for large eddy simulations, where that can be quite a tricky aspect of the simulation. And we've just gone through our first set of revisions for publishing this work in Experiments in Fluids. So I'm hoping that our reviewers will be satisfied with our revisions, and hopefully it should be published soon. So just to wrap up here, I'll talk about what we're working on now, looking forward. So something we're trying to do in the water tunnel now is add these spires and a rough false floor so that we can customize the flow profile that we get to do these city models. So it lets us make a thicker incoming boundary layer, and that'll let us test even larger models. So this is commonly done in wind tunnels. You might have seen this design in different kind of atmospheric boundary layer wind tunnels, but it's very seldomly done in water tunnels, and we are finding it a little bit tricky, but this is what we're working on right now, and hopefully it will work. I'm very optimistic, and the long-term aim of this research is that we want to model Southampton. So I have a team here that I'm working with. I'm a co-supervisor for a PhD student who's doing the CFD of the flow around Southampton, and then I'm the main supervisor for a PhD student who's doing the experiments and who will be 3D printing our city of Southampton and putting it in the water tunnel. So we're trying to push the domain from not just the neighborhood scale, but to get our whole city in there. And I have a postdoc who's been helping design these false floors and do these CAD renderings for the CFD building models. And this is hopefully what we'll be achieving next year. And that brings me to the end of my talk. Thank you very much for listening. And if you're on Twitter, you can find me on Twitter too, and sometimes I post interesting experimental fluid mechanics pictures on there. So thank you very much.
Thank you so much, Dr. Vanderwel. Just waiting if we have a questions. So, minute for that.
Well, also, if you don't get the chance to ask a question now, I put my email up there, so you can always ping me an email.
Yeah, thank you so much. Okay, we have a question from Bilal here. Thank you for this presentation. I'm just reading what he wrote. Okay, so thanks for the presentation, Dr. Vanderwel. I don't understand why you choose to emulate a city urban building structure as a fractal structure. Also, you mentioned injecting dye and doing the PIV simultaneously. Can you elaborate more on that? Did you have to use any seeding apart from dye?
Sure, those are two very good questions. Why did we choose to emulate a city as a fractal structure? Really, we were trying to figure out the impact of the multi-scale nature of cities, and we thought, well, what is the best thing that we can do to represent a multi-scale thing? And fractal immediately comes to mind as fractal properties of having repeating scales but decreasing in size. There's also some literature out there actually calculating the fractal properties of big cities. You'll see that some cities will have like a core, and then the suburbs are almost like a smaller iteration of the city, and we see that repeating and repeating. So that's what motivated us to do to generalize the city as a fractal instead of just picking a city like we did in the second case study. And I suppose to elaborate more on the experimental method. So, okay, let me reread this again. So injecting dye and doing PIV simultaneously, how do we do that? So in order to do particle image velocimetry measurements, PIV, we have a pulsed laser that illuminates the flow, and it's a green laser, and we have seed particles in the flow that reflect the laser light, and you can see these sort of sparkles in the flow, and that's captured by a PIV camera. And to get the best signal to noise ratio, we can even put a filter on the camera that blocks out all the light except for the 532 nanometer light that we get from the reflected green laser from the particles. So our particle image velocimetry camera just picks up the green sparkles that are seeded our flow. Now for the fluorescence, we can use the same laser, so a 532 nanometer green laser, inject a fluorescent dye in the flow, and rhodamine has the property that the peak absorption is at 532 nanometers, but it re-emits fluorescence at 566 or 570 nanometers, so that's kind of like yellowy green. And so we have a second camera that's focused on the same field of view, but this camera has a filter on it that blocks out all light below 540 nanometers. So it blocks out the laser light, it blocks out the reflected laser light being scattered by the seed particles, and it only picks up the fluorescent light from the rhodamine illuminated by the dye. So that lets us take simultaneous PIV measurements with one camera and PLIF measurements, the fluorescent dye measurements with a second camera, and they're synchronized because they're occurring at the same laser pulse. And that's how we do it.
Thank you, Bilal, for the question, Dr. Vanderwel, for answering that.
I hope that was clear.
We have something from Dr. Omid, an amazing talk. Thank you. What's the expected atmospheric Reynolds number and the turbulent intensity range compared to what was used in the experiments?
I'm not sure offhand. I'm sorry, I don't know. But I suppose you could calculate it on the back of an envelope, but I know it's much bigger than we can achieve in the lab. And I guess that's why we are so concerned with the Reynolds number invariance in the turbulence regime, so that we can make that argument and extrapolate our results.
Okay, any other questions? Okay, Dr. Shwari, can you talk? Like, I mean, okay.
I think there's one more question in the chat. I just figured out how it works.
Okay.
So I see that Bilal is asking, how come we chose using a water tunnel instead of a wind tunnel? So the reason we use the water tunnel is so that we can do the fluorescent dye measurements. So I have colleagues that are doing air pollution measurements in wind tunnel simulations, and the way they do that is usually by introducing like an inert gas as the air pollution in the wind tunnel, and then they need to use a fast flame ionization detector to measure the concentration of that gas. But the problem is that it's limited to a point measurement, and you can't take these like beautiful colorful images in the wind tunnel. So the water tunnel lets us use the fluorescent dye, which has this unique property of the fluorescence, and measure the concentration field, making these beautiful colorful images, but also letting us resolve these scalar fluxes in a spatially resolved map. So that's my unique selling point, and that's how I got a fellowship here at Southampton to work on this.
Can you guys hear me?
Yes, hi George.
Hi, Christina. So I just a quick question. We recently have removed the wind tunnel, and we're thinking of putting up a new one. Can you, since you were involved in the building of the water tunnel, I guess, and not the wind tunnel, but do you have some, in the couple minutes we got left, some insights into the difference between, or what would be better if we only had one choice, a big wind tunnel or a big water tunnel? What would be better and why from an experimental point of view?
That's a tough question.
Sorry.
I think we've been having quite a few problems with their water tunnel and the commissioning of it. And it's tough to get the turbulence intensity of the water tunnel down because the pump adds a lot of turbulence. And even if you have screens to reduce the turbulence, they're only effective to a point. So with our new water tunnel that we're building, that's something that we're trying to push down the turbulence intensity to adequate levels. And I think that's not quite so difficult with a wind tunnel. The flow is easier to control in a wind tunnel. It's not the end of the world if it leaks a little, whereas if your water tunnel leaks, that is quite a mess. So I can see you could get a lot more for your wind tunnel because it's a lot less tricky, I would say. And there's a lot of fancy things you can do in a wind tunnel. One thing that we do that's quite fancy in our wind tunnel is that we not only have different grids we can put in ahead of the test section, but we also have active grids. And so active grid is a series of rods with turning vanes, and that lets you have complete control of the turbulence intensity in the test section. So that's kind of cool. I can't really see doing that in a water tunnel very easily.
All right, thank you so much. I think there's maybe one question, but from my end, I think we're good.
Okay, we couldn't hear him, right? Okay, we have another question from Dr. Chuck in the chat. Excellent talk, thank you. And the fractal model it seems that perhaps the smaller size structures may have a negligible impact.
You know what? That is exactly one of the findings that we found in that study. I printed one copy of the model just with all the smallest scales removed, because I also thought that this might be true, and I couldn't measure a difference in the drag to statistically significant uncertainty. So you were definitely right. The small structures don't have very much impact. And it's becoming increasingly clear.
Okay, any other questions from the audience? Okay, Bilal again has a question. Is using hydrogen bubble measurements something visible or even reliable for your experiments?
That's a cool idea. Hydrogen bubbles are fun to do. I dabbled in hydrogen bubble experiments when I was a graduate student, and they're really good for highlighting some of the structures in the flow. But you know what? I think fluorescent dyes are even better. So since I've been started working with the fluorescent dyes, I haven't gone back to using the hydrogen bubbles.
Dr. Chuck is saying extend your work to wind farms.
We could. I have colleagues at Southampton who are doing that sort of thing, so I don't want to step on any toes. So this is why I'm focusing on the air pollution aspect, and colleagues of mine are doing some wind farm work in the wind tunnel.
Any other questions? Okay, if not, we want to thank you, Dr. Vanderwel, to be here today. Nice talk, and I want to say congratulations for your ebook coming soon. You mentioned at the beginning. It was nice meeting you. Thank you so much.
Well, thank you for inviting me, and also thank you everyone for the really insightful questions.
Yeah, thank you.
Thank you.
Okay. Thank you so much, and have a good day, everyone.
Thanks, Bilal. Thanks, Karim.
Yeah. Bye-bye.